provided on the website. There's also information about non-focus project within the website, which is the new home of OpenMBE. And if you're interested, you can also look into ways that you can contribute to this efforts by reporting bugs, pull requests, etc. All of these are documented within the OpenMBE website. And if you're looking to participate in the community, there are lots of resources available. You can join Google Groups and Slack, which is pretty active, I will say. And we have other resources within the OpenMBE community. And I just wanted to point these out in case anyone is interested and would like to look into more information after this session. They can also find information about the licenses, etc. And after that, Bryan will be covering the current status of OpenMBE projects. He'll go into details of the current studies as well as the MMS and Flexo updates. We'll also look into the project portfolio of where we will cover the OpenMBE architecture as well. And then after that, we'll be finishing off with the industrial scale project, which is the 30-meter telescope example, which is currently being developed by TMT Observatory Corporation, but it is available as an open source for whoever is interested in a model-based systems analysis with SysML. This project leverages an extension of Incose's OSAM and will provide more examples on that as we go by. And then we'll open the session up for questions and discussions from the participants and contributors. So without further ado, I'll start with our presentation. Please let me know when I go into the slideshow mode if everyone can see it, or should I stay in the browser look? How does this look?
We can see it.
Awesome, great. As I mentioned, OpenMBE community is centered around open source model, and it serves as an enabler for systems engineers, and it helps to close the gap between the models and several engineering artifacts or engineering documents, and it's adopted by a larger community in the industry and academia. This presentation has been given before in the community by Robert Carban and Chris Daub, which are the leaders of the OpenMBE movement in Jet Propulsion Laboratory. And I'll be covering their slides for your information throughout this tutorial. Yes, and the overall motivation behind OpenMBE is to support systems engineers by providing means of concurrent collaborative design environment. Systems engineering is an interdisciplinary engineering branch in nature, and therefore collaboration is the key in building modern and complex systems. And we have today highly complex and interdisciplinary systems that drive the need for a more collaborative environment. And therefore, there's a need to move from a traditional way of doing systems engineering, which is document-based processes, to a more digital world. Systems engineers also need to drive the leadership through effective communication. This leadership also has major challenges in a more traditional setting. Systems engineers also need to artifact and design these complex systems, and managing this complexity requires being able to represent the complex systems with their complexity. So it's hard to facilitate this environment with documents, paper-based documents, without the explicit links and traceability option of engineering artifacts and documents. And what you see here is a large team, and flight project teams are typically very large. And this is just a portion of the Mars sample return team here at JPL. And as you can imagine, it takes a lot of people for a single mission, and teams are growing larger and larger. And paper-based documentation, which is the typical thing for systems engineers to generate, created the challenge for engineers to keep track of the current designs and their changes. Plus, complex systems, the modern complex systems require more information today. And cost of creating information used to be very high without the digital means, but today we can support this. The documents can be created in a rather cheaper way and in a fairly easy way too. But that also brings about as problems, as everyone can create their own digital copy with different variations and updates, if you will. And it can end up in a nightmare for systems engineers to continuously search for the most updated information to update their documents, and then at the end deliver this the engineering documents in the most updated version. So when we start a project, typically we have a few documents, a few engineers and a few documents. And the project teams iterate on these models and documents. And systems engineers enter this data into their rollup. And they edit to a document and then get input from others. And this cycle grows larger. The interactions between the documents and engineers grow larger. For that, more people keep being added to the teams, and more documents and artifacts are created as the time goes by. And information and models keep getting more and more complex, as well as the task distribution between engineers. And before we know it, it's an overwhelming number of engineers and documents that are produced. And it becomes overwhelming for a single engineer. You can see in the middle with the orange head. It gets overwhelming for any single engineer within the team to access and locate the most updated information of the project and understand what portion of this information each engineer needs the access to. And this is one of the calls of our engineers in JPL. Most of my job is the data entry, and I want to do real engineering, which is understandable because it becomes a challenge for systems engineers, especially to keep track of the data and the information. And it creates an inefficient thread of utilizing the engineer's time. So another quote here says, using engineers as information generators may not be the best use of their skill, which I think all of us can agree on. And ideally, we would like to have less overhead and focus more on the novel engineering work by avoiding the repetitive data entry and preventing version confusion, and maybe spending less time on constant searching of the data available. And these may not add up to the most efficient way for engineers, systems engineers to spend time on. They rather do real engineering. They rather contribute in more novel ways to the project. And hence, a better way of managing this complexity of modern projects would be having collaborative models with version control and linking all this clutter, all these documents that are generated to the models. And this is a lot more manageable. The representation on the right-hand side is a lot more manageable than the clutter we have otherwise. for example, the file versions may be continuously being changed through emails and local resources. And instead of that, we can actually have direct data syncing, which will save engineers a lot of time for spending less time in constant searching of the information. And therefore, we say a better way is to have the right software to maintain all these complex relationships between artifacts. And this way, it becomes easier for systems engineers to navigate through all this information. And this is really the driving motivation for OpenMBE, where the information is connected within and between documents, and the manual and unconnected data management is prevented, which would mean a paradigm shift towards a single authoritative source that facilitates connectivity between these various engineering artifacts, may it be a model, may it be just a document, etc. And having a single authoritative source also enables the tracing of documents and propagation of change, which provides engineers with more vigor. By threading the engineering work and the documents and other artifacts together, systems engineers can save time on generating documents with the most up-to-date information. And this illustration is very meaningful because it conveys the concept of user experience that is envisioned within the OpenMBE community and environment. So for a user, this digital framework allows for a model or document to be updated once, and it will be changed everywhere, which is pretty time-saving if you think about the data inconsistency that might occur otherwise. And everyone will be referencing the same information between the engineers who work on the model or versus the engineer who's responsible for creating the documentation. And the software here is responsible for the synchronization of the data, where any update to it may be coming from different tools. And here you see the different components of OpenMBE. Again, it's not only about a software platform, but it's also about providing guidelines to these engineers to show how the environment can be built with real-life examples. And OpenMBE has the model management system, which is the core repository that manages the federation of references and provides version control. And we also have the View editor in this environment, which is a document-based interface that allows for documentation of the model without having to need to interface with the model necessarily. And it provides a web-based environment for that interface. We also have the model development kits that facilitate the integration of various modeling and analysis tools, which lets the engineers have a united environment. And a popular MDK that you might heard of could be the Magic Draw or Cameo Systems Modeler or MATLAB. And there are lots of examples of model development kits out there. Additionally, as I said, there are lots of documentation and training resources available within the OpenMBE space, as well as an open source example of the 30-meter telescope model, which we will cover through the end of this tutorial. So we'll deep dive on this part as well. And we also have the OpenSE cookbook, which provides a collection of best practices for modeling with examples. And all these enablers, all these parts of OpenMBE really provides the engineers, systems engineers, with the information and examples to get started with OpenMBE. And now I will pass it to Bryan, my colleague, to give you guys a little bit more information about these different portions here, such as the model management system, View Editor, and MDKs, and then we will go over the 30-meter telescope model at the last portion of this tutorial. And if you have any questions so far, we can take that as well. So let me know how you want us to proceed.
Some question? I think you can proceed, please.
Right.
Okay,
Bryan?
Yeah, I'll go ahead and share my screen if we're able to change that. Okay, can you see my screen here? Should be the same slide.
Yes.
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 Okay. Yeah, so I'll go into detail these products that we've developed. And like Fatma mentioned, here at OpenMBE, we develop different tools to support systems engineers. And before I do a deep dive on these individual tools, I'll give a brief overview of where we're at and our current status of our projects. So in OpenMBE, we name our architectural release cycles. And if these names seem familiar, they're from Futurama robots. And currently we're on ExecuBots, which encompass MMS4, View Editor 4, and MDK5. Previously, we had DOMBot, which was MMS3. And we're working on a new architecture, Flexo, which I'll go into detail in a bit here. So with ExecuBots, we support relational database, support Spring Boot, support any S3 compliant storage. We have an Open API 3.0 spec, read to docs, horizontal scalability with Docker. We have a point-in-time reference for models. It facilitates model dependencies, artifact version control, and Jupyter Notebook support. Again, in ExecuBots, we have these model-based architecture, and I'll go into detail later more of what it means to add a model to MMS4. We provide a reference implementation of how to deploy your MMS4 instance with something with Docker images and how you can containerize this, and as well as differences between different architectures. And all this information is here in our wiki. We have the differences between MMS4 and MMS3. And quickly, I want to talk about our Flexo architecture, which is where we're going. And so our Flexo architecture, the idea is to have a graph-based data store as the layer 0. And then services could just build on top of this. And with something like Sparkle or with REST, you can communicate with them as needed. And the big thing is that it's schema agnostic, that build upon existing standards and an interface for information to exchange all the layers. And this layer cake is not necessarily boundaries. It's more just a conceptual diagram of how the Flexo architecture could work. And currently we have MMS5, and we have developed a version of View Editor that works within Confluence that I'll go ahead and give a quick demo of that. So here you're inside a Confluence page, and we have developed a way so that you can interact with the model that is in MMS5 by inserting cross-references. In this case, what we have stored in MMS is requirement data. So here, for example, you're referencing a requirement from DNG, and we provide tools to extract requirements from DNG and load them into MMS. Here you're specifying what it is that you want to display on this document. And the main idea is that you're composing these engineering documents from the model data that you have in MMS. And this is all within Confluence. So you specify that you want the requirement name, the text, and the ID. And when you publish this page, you have these elements available to you, and then you can quickly move over your mouse and a tooltip pops up with that information. And this just provides an easier way to read requirements. So another way that you are able to display requirements is by creating these tables, and this video will go and show that in a bit here. So here we have these tables, which this is another custom element that we built at OpenMBE. You can specify what you want in this table, different requirements. You can see the version of when the data was taken out. Here you see September 1st, 2022. And you can publish this table. And then your requirements can be reviewed by someone else here within Confluence. You can also link to the requirements. And make updates. So this is what the Flexo architecture enables, to be able to make this these types of updates in Confluence and show these presentation elements. Now, if we go back to our current architecture, to our Flexo architecture, our model management, and Fatma touched on this briefly, MMS provides services for managing models and is a version control system for structured data. It exposes model information through a REST API. It allows for CRUD operations like branching and tagging of the model repository, and the ability to add these different Spring Framework-based modules depending on each project's need. And what that means is, for example, if your organization has LDAP authentication, you can add an LDAP module to MMS. Or if you want to store artifacts in S3, you can add an artifact module to MMS. And all of these modules are plug and play. We provide a guide on the reference implementation on how to add these modules. And one of our popular ones is the Teamwork Cloud module, which syncs up your model information with Teamwork Cloud. We have our View Editor platform, and View Editor enables you to interact with models within a web-based environment. It interacts with MMS's REST API and provides a web environment to create, read, and update these model elements, including documents and views. Data and different modeling tools can be shown in a primary narrative format on the web without losing the connection to the data sources. And we also provide these model development kits. One of our most popular one is this Cameo Systems Modeler, or Magic Draw MDK, which interacts with MMS and implements what we call the DocGen querying language. We also have other MDKs like Jupyter MDK and MATLAB MDK, as well as a Mathematica MDK. And I'll give a bit brief overview of how it is that these services interact with each other. So here we have an example of these model development kits interacting with MMS, and you're able to publish models and read models from MMS. And then View Editor can also read and publish and update these models. Here's an example of just two different clients. We have Jupyter on the left and Cameo down at the bottom, and they both interact with MMS. And then this gets published to MMS, and you can see them in View Editor on the right. Now, as far as that Teamwork Cloud module that I was talking about, how it works within Cameo Systems Modeler Magic Draw is that we coordinate a sync so that whenever you commit to Teamwork Cloud, you are also committing to MMS. And when you make updates from View Editor to MMS and you pull those with MDK, we coordinate also the models so that they're mirrors of each other. So this is how it works with that Teamwork Cloud module. And I'll go into a little demo on how it is that you create these presentation elements for View Editor. So you have these beautiful SysML models, but what now, right? So we need a tool that could visualize this information in a familiar format. People like to see documents, slideshows, and tables. Information needs to be reviewed and updated by people that don't want to interact with the model and needs the ability to keep model consistent by leveraging cross-references. And you don't want to ask maybe a subject matter expert to just download Cameo and interact with the model that way. Maybe the best way might be to just have them review a table, something that can be shared as a link in the web browser. So when you install MDK on Cameo, you have a lot of new options that are available to you. One of the new options that you can generate these new view diagrams, and you have new options for MMS and DocGen. These are all added as part of the plugin. And the big idea is that you create these view documents, and you have documents and views and viewpoints. So for example, here on the left, we have this view diagram, and it has a document on the top root. It is composed of views, and these views each expose different parts of the model. So for example, at the bottom, you see it exposes this blocks package, and then on the top, it exposes a diagram. And we have these viewpoints. And on the right, we have what is the DocGen querying language. And what this does is you start at a node, you collect the on element, which is whatever is exposed by that view. So for example, the blocks package. Then you filter by stereotype, and you filter of type block. So it would grab all of the type blocks inside of this package. Then you would create a table structure and specify what it is that you want your table attributes columns to be. In this case, we just want to take a look at the name, and you filter out the name property. So once you create this viewpoint, you create this DocGen diagram, you create this view diagram, you publish it to Teamwork Cloud, which coordinates a sync with MMS. This table gets published to View Editor. And in View Editor, you can make changes to that same model, and making changes to the name here would update that property back in the model. And here it just shows how you update the model by making a commit. Making a commit to Teamwork Cloud makes a sync with our MMS instance and keep things synced up. So this is just a quick overview of how it is that you create these documents. But for all of this information, we actually provide user guides. So we have our DocGen user guide, and these are manuals that get installed in once you install a plugin, or you can take a look at them in our website. And here we provide detailed information of how it is that you create all of these presentation elements. So for example, if you want to add a paragraph, we show how you can do that within the DocGen querying language. So all this information is available to you. And another example here of using MMS with maybe an auxiliary tool would be, for example, with ML. You have your master's equipment list, and here I'll show a quick demo. So say, for example, you have your master's equipment list, and you have here a component You change it. This is synced up with the model. You change the mass. Then you can have an auxiliary tool, like here in this case, we have MapleMBSE that's connected to the model. The update is carried over here. This helps for people that want to work on Excel. You can insert another component. And that shows up here on View Editor. So that is a brief overview of MMS, View Editor, and MDK. We have our OpenMBEE cookbook, which is available in as a URL that you can take a look at as a View Editor. We provided a guest account to take a look at that View Editor, as well as a model for that. And for all of these tools, they're open source, they're in our GitHub. And like Fatma mentioned, you're able to contribute. We have a Slack channel that is pretty active, and resources on how to contribute on our website. And with that, I'll hand it back to Fatma to talk over 30-meter telescope.
Thank you, Bryan, for the great insights on these other components of OpenMBEE environment. If you can stop sharing, I'll share my screen. And awesome. Taking me a while. There we go. I hope you guys can see my screen.
Yes.
Awesome, awesome. Yeah, again, thanks, Bryan, for the deeper dive into a bunch of different aspects that we can look at when we think about the collaborative environment that OpenMBEE offers. Right now, I would like to go into a real-life example with the 30-meter telescope model, and then after that, I will give some more information about OpenMBEE in general, and I will open up for questions and discussion points. So without further ado, let me share the 30-meter telescope slides. As I said, it's 30-meter telescope is completely the models are completely generated with systems within the systems environment, and this is an open source model. You can see capture of different operational behaviors within the model that includes subsystems, identification of interfaces, and definition of interactions among different subsystems. And there are also examples in the model for developing and refining timing requirements by using different algorithms and external interface commands. And it also provides examples of executable system model with state machines and activities to specify behavior of each use case. And we use the model to analyze the system design and verify the initial requirements on power consumption, mass time, error budgets. We have Monte Carlo simulations for the probabilistic timing analyses. And we are also able to produce engineering documents within the TMT systems engineering efforts. And these are stored in the View Editor, which I will showcase in a minute. And we are also using standard languages and techniques and to avoid custom software development, and provide an example to these systems engineers that you can deal with the existing standards rather than putting extra effort into developing your own customized software. And as I said, the environment allows to perform different analyses, and we can run this already set up configured analyses with a simulation engine, where the initial conditions are given to the simulation configuration, and then we are able to receive the final conditions after running the simulations. And we can produce the analyses declaratively in a reproducible way without any single line of project-specific code. So again, customization is avoided as much as possible, which reduces the time and resources that are required to do systems engineering. Also, by avoiding these customizations, certain customizations, we are able to transfer knowledge in a faster fashion between different engineers, because the company or the corporation can hire new engineers, and it is harder to transfer all that knowledge when there's so much customized tools and libraries within our model. So it helps with that as well. And as I said, the simulation engine creates the views on final conditions, and the results can be displayed in various ways. As you can see on the right-hand side, we have different display options within our environment, and the table showing final analysis values here. The example is about the peak power, and we can also observe pass and fail status for each scenario by refining the requirements as mathematically expressed constraints. So that way, it provides an automated way of checking the requirements. And we can also observe the state changes of the components over time by looking at these timelines and how the, each state is changing. The lights can be on and off in different times, and we are able to visualize that for the engineers to see what state at each component is within the system. And we can also have value profiles that rolls up the total values over time, which uses certain patterns, which are also described in the OpenMBEE cookbook if people are interested in static and dynamic rollups. So feel free to look at those, and if there's anything of an interest to your projects. And we also have system level Monte Carlo simulation for compliance. So on the left-hand side, you see an example of a behavior within the TMT model, where we have different actions that are executed within this activity diagram. And Monte Carlo analysis is used with different operational models and probabilities for different flow to check the compliance of the capture scenarios against the requirements. So the system model captures the functional and physical architecture, behavior requirements, and parametric relationships for the TMT acquisition sequence example here, and related use case scenarios at the system level. And operational modes and behaviors are modeled using activity diagrams, as I mentioned, and scenarios are typically captured using sequence and activity diagrams as well. Verifiable requirements are formally captured using constraint on properties. So on the table on the right-hand side, you see a compliance summary. We have different time results for each group of simulation or for each configuration, and we're able to see if we satisfy the certain requirement or not. For example, the red indicates that requirement, that particular requirement has failed to be satisfied, but the rest of them seem to be a pass status. So we also have a specific scenario analysis result here, showing which component is in which state at a certain time. as I mentioned briefly before, so we can see if any component is in the wait state or taking exposure, change filter, and we have another wait state here. So it's very useful for engineers to be able to simulate all this at once and see what state each of these components are in at a given time. So we are able to provide that. And we also have a workflow that enables automatical verification with the behavioral specification against the time, power, and mass requirements. For example, here, when we have a change request for our requirements, let's say the number of exposures of 45 seconds is changed from 6 to 4. These change requests can be easily updated within the system model, which is also not only expressed in a text format, but also mathematically formulated within the constraint elements. So we can say a certain property needs to be less than or equal to than a certain property. And by giving that, we can analyze our conceptual design pretty easily by running our simulations and analyze and realize the changes that comes with the change request and observe if we have passing or failing cases once the change is made. So this way, since one change is made at one place, propagates through the rest of the system, we don't have to redo all the steps to verify our requirements. Rather, we change this particular property and the change is propagated throughout our system. And then after our simulations, we're able to see if the requirements are satisfied or not, as most systems engineers need to obtain pretty quickly. We also have engineering documents that are generated and embedded mutually consistent model information and analysis results. So whenever this platform, actually the Viva Editor platform, not only provides a user guide for the engineers or some presentation aspects, but also provides a platform to publish their results or generate their reports for review. Now that we show a picture of the screenshot of that here, I'm going to switch to a real-time Viva Editor page for this TMT model, which is again accessible to OpenMBEE community. As you can see, this is the Viva Editor page for the OpenMBEE platform, and we have several documents for the TMT model here. If you're interested, please take a look, and you'll see different ways of publishing these documents as well. There are many examples. And I just want to start with a quick example for everyone to have a better idea about what you can publish or generate within this Viva Editor environment. So I open up the use case development document here, and it has several subparts and sections, and we are able to scroll through or just like click and see each of these parts. And we are also able to not only describe the model organization or defining the behaviors in state machine and give information to engineers, but also we are able to extract the source element from the Viva Editor. What I mean by that is when I look at the preview element option here and I click on this diagram, for example, I'm able to see the element ID that I can search within my model, within my systems model, and that will, by doing a quick search with the element IDs, I will be able to go to the source of this diagram and make any changes as needed, which is this particular diagram is taken as the image, so I cannot make a change on the image, but I can go ahead and change it in the model and then update the documents. But we also have several tables within, I'm sure I'm going to run into an example, but we also have several tables that we use within the View Editor page that can be updated on the View Editor side without interfacing with the model. I'm going to give an example of that as well, but I just wanted to show the overview of what a user can show on View Editor. So we can start with an introduction, we can educate people on the model organization, we can talk about how we verify our requirements and where to find the results. And then at the end, we can talk about how to generate these documents. Here's the, for example, duration analysis example is given within this image. And we talked about publishing results. And one example of that, let's say if we go to the time to execute one, and we have a table here, which is collecting, as Bryan described, collecting the information that is in the model, collecting the simulation results, and posting it here as a table where we can visually see all the results that are the product of our simulations. So for example, we have a time limit here, which is 7200, and we see the resulting result of the simulation is less than that. So this would potentially satisfy the requirements. So we can publish all sorts of results within the View Editor page and inform the designers. And this is also direct sync. So once something is changed in the model, we'll be able to see the change result on the View Editor page as well. So we are also able to, again, publish the different views from our model without actually going into the model, which also helps with the navigation of people who are not necessarily familiar with the system model. So they don't have to open the model, they don't have to download Magic Draw or Cameo Simulation, CSM, sorry. They can just go into the View Editor page and read what they need to read, and that's it. So it provides a great platform for high level or lower level engineers. They can look at different things. One can look at the system level, one can look at the subsystem level. Yeah, this is pretty much what I wanted to show about the View Editor page of TMT. Again, this is available to the users, available to the OpenMBE community. So please feel free to see if you have any interest in this. And having concluded that, if there aren't any questions so far, I would like to go back to our presentation and continue with the more detailed information about the OpenMBE community and its industry adoption.
We have 40 minutes still.
Sorry?
We have 40 minutes, yeah.
Okay, yeah, we have the time, I think. Yeah, I will cover the rest of the slides and then we can open it up for discussion. Yeah, so one thing I wanted to mention here is that OpenMBE has adopters and contributors within the industry and academia, and it has grown into a rich community. It is used in a variety of projects at NASA, as well as other science and engineering projects, such as the 30-meter telescope example, which we just talked about. Industry also has adopted the OpenMBE platform, and Boeing, Ford, and Lockheed Martin has great efforts in that. It also has been part of the standards, including SysML version 2 by the Object Management Group, and commercial vendors also have adopted OpenMBE with integration to their specific tools, which again has been instrumental for providing users for with capabilities and commercial tools along with the OpenMBE itself. So it has been growing pretty tremendously. Also, I would like to talk a little bit about its impact on some example flight projects here at JPL. JPL used OpenMBE on Europa Clipper first with 100 users, and more than 200 documents were generated. And one important thing here to note is the number of connections that were identified. This is particularly important since these connections were not exactly tracked historically due to implicit links of the traditional documents. Now we can, in a way, quantify the complexity of our system by looking at the number of connections between the elements. And the positive outcome of this project was the reduction of overhead by decreasing the time to produce the engineering document. And with that, the benefits of OpenMBE was quickly realized in this Europa Clipper project. And yeah, this is a commentary from one of the engineers in the project. They say the mass and power equipment list produced by the model provided crucial support to their key mission architecture traits, and the key enabler of this model and capability came from the components of OpenMBE, which is great feedback for OpenMBE users. And another flight project that utilized OpenMBE was March 2020. The project had 50 users and over 90 documents and decision gate deliverables. Those documents included the electrical function list and electrical function block diagrams, etc. And the positive, the highlight of using OpenMBE in this project was the technical rigor that was enabled with OpenMBE. Detailed modeling and traceability between systems and their subsystems provided rigor to the engineers, so high fidelity connection tracking was enabled. And tracking of deliverables was also one of the highlights of OpenMBE use in this project. And this is again one feedback from the engineers within this project, confirming that the entire project and the documents that were shared with the entire project and were used as the authoritative source of truth for key deliverables, such as the electrical function list and all, were very useful. And at the enterprise level, I'm sorry, this is the international standards impact of OpenMBE with the digital transformation. And the over 60 organizations and 30 contributors and more than 100 consumers are utilizing OpenMBE, and the OpenMBE community is working closely with the OMG for the development of systems modeling language version 2. And there's more information you can find about that on the website as well. And again, another feedback from Mr. Frandl is the capability that OpenMBE provides is helping to dramatically shape the direction of MBSE, and is turning out to be a critical enabler of MBSE as part of the digital transformation. And I'll also like to talk about the enterprise scalability. And at the enterprise level, Boeing and Lockheed Martin has adopted OpenMBE pretty successfully across many projects, and they demonstrated the enterprise scalability. They had around 1,000 concurrent users, 50 programs, and for Boeing, and 100 concurrent users in Lockheed Martin, which is a good proof of concept. Again, another feedback from Brittany, John, and Barry over at Boeing. The architecture of OpenMBE proves to be enterprise scalable and has so far greatly satisfied our operational needs, which is also a success story for OpenMBE. And not only industry and on the academia level too, there have been inter-organizational collaboration. And here you see the Systems Engineering Research Center also utilize OpenMBE for their data item descriptions and contract data requirements list, etc. And this is from Dr. Blackburn, and saying the use of OpenMBE V1B points as means for replacing a digital sign-off directly with the model information provides the needed evidence. And not only that, but not only at the intra-organizational level, but also inter-organizational level is important to mention here. The future goal of OpenMBE is to achieve a global ecosystem, a digital fabric that where the engineering information can be connected globally in a seamless and collaborative fashion. And one example of that is the Mars sample return concept, where we have different organizations and centers globally, and it's being inter-organizational application for OpenMBE. And this global vision will provide engineers with the option to cross-reference or the reach for data, updated data pretty easily, and it will provide connected engineering information for a connected world. And again, OpenMBE is a community for open source modeling software and models. It has over 400 members, and it actually started with some core software that JPL started, and it continued growing with many contributors globally. And some of the participants to note here are, of course, JPL, Boeing, Lockheed, as mentioned, and as well as OMG, Georgia Tech, and ECO. And this is one of the updates of the OpenMBE community. Has a new home with NumFocus, which is an organization that supports and promotes open software, such as Jupyter, which you might be familiar with, that also plays a key role in SysML version 2 efforts. And OpenMBE is gaining popularity and as discussed in several workshops, in COSA workshops in particular. And it's definitely a growing community within the systems engineering world, and continues to transform the way we do systems engineering by overcoming the challenges that comes with managing complex systems. And having said that, this brings me to the end of the presentation. So Bryan and I would like to hear any feedback or questions that the audience have.
Thank you very much.
Of course.
The presentation was very, very impressive and very interesting. Some question by the audience, please.
Hi, I would like to ask some questions. First of all, thank you so much, Fatma and Bryan, for the talk. It was very interesting and give us an idea. I know there's so much details behind that you could not talk here in this presentation. So many things, and I see OpenMBE as a great opportunity for the formal methods community to apply the strategies, the techniques, the approach that we develop. Sometimes we just work in our rooms and we just have the opportunity to apply in real world scenarios. And in OpenMBE, we have the TMT case studies, which is a real world case study, very large. So for instance, if you work with requirements, there's tons of requirements there. If you work with behavior, there are several behaviors there that describe in terms of activities or state machines, etc. So, but my question is, if I'm a formal method guy and I have some analysis technique, for instance, that I'm developing, and I want to maybe integrate with OpenMBE or apply with OpenMBE together, and I would like to know what your advice, which models, for instance, should I have a look first, and how could I enter in this world and try to integrate my approach into the OpenMBE environment?
Yeah, that's a very question. If we are talking about starting, without any prior knowledge to OpenMBE, I highly recommend these quick start guides. If you can see my screen, and where step-by-step guides is included for each of these OpenMBE components to install them and run them and integrate within with your model. So I would recommend starting there, which is also, again, very easy to get within the OpenMBE website. That definitely would be my recommendation as a start, to go through all these and see what would be the best fit.
Okay, but for instance, if I want to gather some data from the models or from the information on the projects, I think one of the main modules that I have to have a look into is the MMS, right? Don't you? What was your opinion? And that there's some MMS material that you could, just point out, maybe.
Yes.
Yeah.
I will give that one to Bryan, actually.
Yeah. I think here for getting started with MMS, probably MMS RI is your go-to. Here we describe implementation and how to deploy MMS. And here we also specify how to do it as a Docker container, which is probably one of the easiest ways to do it. But yes, you're correct. You need an MMS instance for someone to want to start trying out some of these things. And maybe they might not necessarily want to start off with Cameo, but even with Jupyter MDK, that could be an easier entry point. But I think as far as getting started with MMS, the MMS reference implementation would probably give a lot of information for that.
Okay, thanks. And for instance, if there is MMS with the TMT inside it, so for instance, we could just recover some data from TMT and, for instance, do some transformation to a formal notation and do some analysis.
Yeah, I think like a shared model, is that what you're saying? Like a shared MMS with other.
Yeah, but there is an open server where we could access the TMT, right? In the MMS.
Yeah,
correct.
And you're able to make a REST API calls to that server and get information that way. I think it's like depending to what access is given on those servers. But yeah, we have an open API specs document that shows how to get model elements out of that.
Okay, great. Thanks.
Awesome. Awesome. Any other question?
I would have had almost the same question. In fact, I guess Lucas's emphasis was more on integrating with OpenMBE. So this API to access the models would be more interesting to somebody who's developing analysis softwares, because we will have to query and probably transform, do the analysis, back annotate the results, write it somewhere. So not as a user, but as a developer, where should we start if we want to integrate our solution with OpenMBE? Is it the same thing?
Well, I think so you're a developer that wants to integrate with our already existing models as maybe as a read only, possibly update. I think identifying which MMS instance you're using, right, to reading from the models and accessing that open API spec from there, and you can take a look at what are the routes that are available to you and what are the elements that you can update. I think if you're a developer trying to make changes to the model, because that's what the Jupyter MDK does. We also provide a client for Jupyter that is just the API specs that you can use within Jupyter to make these calls. So actually, maybe I think I can have a quick demo here, Fatma, of or actually,
Yeah,
can
I
you go
was
back to
thinking
the
the
tutorial
same.
page?
Yeah, I was thinking the same.
This
that's right.
MMS Python client, yeah. So here's an example of
Yeah.
it interacting with the API.
I can play it.
This is an example notebook. You specify your server, your MMS server, your project. You log into your MMS server.
Okay, that's for the password.
And here we have the specific element ID that you're looking at. You're grabbing the title, and there's no documentation. Here you're changing the model. And you can publish documentation. So I hope this answers the workflow that you were thinking. You're able to, yeah, you're able to interact with the model with something like Jupyter. And we have a generated client that is generated from this open API spec that is on our OpenMBE GitHub or on should be on our website.
So if I understand correctly, I would use Jupyter to instrument the interaction between MMS and my tool or my service.
Yes.
So
Or a
query the
Python
models and feed it to.
or any Python client.
That's great. And my other question is about whether you have any formal methods, tools integrated with inside OpenMBE, some kind of model checker or theorem prover. We heard about those a lot. Anything for the analysis or formal analysis of behavior, for example?
Is there something that you can think of that we use Fatma for TMT?
No, we don't really have a model checker, as far as I know.
I think maybe this is where things like vendors come into play that integrate with OpenMBE. I know that there's been some model verification with inquiry that is connected with OpenMBE. So maybe you could see that happening on that end of other connections.
Right. Yeah,
Okay,
but
thanks.
that would be a good future direction, actually.
I would actually encourage the audience and the community, because this is so the reason why we actually wanted to include OpenMBE in the program. This is some behind the scenes information from the PC shares, is that we really think that this kind of openness and the unification of the methods and models in the systems engineering domain could be a really good application domain for formal methods, because before this we could integrate with the Cameo, for example, or Magic Draw, but that was only a tool, and it wasn't really worth the effort for academia, for example, to integrate with a proprietary tool. And with OpenMBE, we actually could have a window, so to say, to real applications, to industrial partners, and this could be a really good way to leverage the technology that we are working on, we are developing in the formal methods community. So I would encourage all the people here to investigate this opportunity a bit more.
Yes, and you all can look into ways you can contribute, and you can instantly become part of OpenMBE community by just joining Slack. So yes, thanks, Vince, for the remark. Yeah, we really encourage everyone to take a look at different means, options that they can contribute, or if they want to adopt this environment. And yeah, you'll see several resources here as well, like YouTube videos, lots of GitHub sources and view editor pages and Google Drive. So there are a lot of documentation out there. So I also encourage people to take a look at those.
I have a question. Robert said that CSUML is a formal language, and you adopt CSUML to specify models. How difficult has been the adoption of CSML by the engineers in GPL?
Yeah, I think that's a very interesting question, and I think that's something a lot of industry partners also struggling with, the adoption of SysML. I wouldn't say within our team at JPL, I wouldn't say there's any resistance towards SysML, but I can see that how it can be a little bit more difficult in certain circumstances. I mean, I can only talk about my personal experience, and I will say, and JPL was pretty accommodating for the SysML adoption. But I also understand that requires the shift and a cultural change as well for the adoption of SysML. So that's actually a very interesting topic that to bring up and to discuss. How can we make it easier for engineers to adopt the use of SysML? And also SysML is changing too. Now we are moving towards version 2. I think, again, being tool agnostic and understanding the use and the methodology behind it is really key.
Okay. Thank you very much. So another question. Please let me to see if in Discord there is some question. Just a minute. No. Okay. Thank you very much for your ability to present this your work. Really is a work very interesting, and I think present to us of the formal methods area some very interesting examples and motivation to work in things that you are doing. Thank you very much.
Thank you as well for inviting us and giving us space in your program to present all these aspects of OpenMBE. Thank you.
Thank you. Yeah.
Okay. See you tomorrow.
See you. Thank you.
Thank you.
Bye-bye.
Bye-bye.
Bye.